Hello, welcome to Chapter 9, Sampling Distribution of Sample Means, Confidence Intervals and Hypothesis Testing. In Chapters 7 and 8, we worked with confidence intervals and hypothesis testing for a population proportion and for the difference between two population proportions. In all these cases, we used the normal model. In this Chapter 9, we will study the same, but not for the parameter proportion, but for the parameter mean or average. Notice that the transition from proportions to means equates to the transition from categorical variables to numerical variables. If we are studying about, for instance, income, which is numerical, we usually care about the mean. If we study about gender, there is not such a thing as the mean gender, because we cannot add the value male with the value female. In the case of gender, the parameter of interest is usually the proportion of women or the proportion of men. We will see that with numerical variables, it is important the standard deviation, a concept that doesn't apply for categorical variables. And we will see that in many occasions we need to adjust a bit the normal distribution to make it more loyal to reality. This adjusted version constitutes a new distribution called T or student distribution. I will introduce some new concepts as I go over the exercises. Exercise 1. We have a population of college students in which the mean age is 22 years, with a standard deviation of 3 years. For this population, we pick many random samples, all of them of size 100. This population could be the same as in Chapter 7, Exercise 1. The difference is that there we were interested in the proportion of women, and here we are interested in the mean age of the students. Letter A. Each sample may show a different mean, but what pattern will we see as we continue to pick samples like that? To explain this, I do with my students a dramatization of a simulation. I will go a little fast because it's pretty much the same as we did in Chapter 7. I ask one of my students to imagine that they pick a random sample of 100 individuals from this population and to tell me what's the average age in that sample. The student tells me 19.5. Notice that the Greek letter mu denotes the parameter, the mean in the whole population. X bar denotes the statistic, the mean in a sample. And I use a subscript to express one particular evaluation of the statistic in one particular sample. I do the same with other 3 students and they tell me, in my sample the average age was 21.3. In my sample the mean was 23.7. In my sample the average was 18.8. Then I represent those 4 means in a dot plot and I ask the students simple questions. Are all these means possible? Yes. Are they equally likely? Usually all the students answer no because they learned from Chapter 7. Among these 4 means, the most likely is 21.3 and the least likely is 18.8. The reason is that random samples tend to be representative of the population. Since the population mean is 22, random samples will tend to have a mean around 22. Now we can answer letter A. As we continue to pick samples like that, we will see that the average 22 appears more often than any other average. And the averages close to 22 also appear more often than those that are farther above or farther below. This is the idea of a bell shape. In other words, the sampling distribution of sample means will fluctuate around 22 with an approximately normal shape and a standard deviation of 0.3. Where do we get this 0.3 from? The theory says that in a situation like this, the sampling distribution of sample means follows a normal model whose mean is the mean in the population and whose standard error equals the standard deviation in the population divided by the square root of the sample size. Since our population standard deviation is 3 years and our sample size is 100, the standard error will be 3 over 10 equals 0.3. And like I did in chapter 7, here I will not prove this formula, but I'm going to try to make sense of it. It seems clear that in a homogeneous population, samples vary less. For instance, if we pick samples of students from second grade, the mean in the samples will be essentially the same, because students in second grade have the same age. On the contrary, if we pick samples of college students, the means will vary more because college students vary more. The variability in the population is measured with the standard deviation and affects directly the variability of the samples, so the population standard deviation shall appear in the numerator here. It seems also clear that small samples vary more than big samples. If you pick a sample of 1 or 2 students, everything could happen. Maybe you pick 2 of the youngest and the average is very small, or you pick 2 of the oldest and the average is enormous. If you pick a sample of 100 students, it is much less likely that you will pick only young or only old students. Samples of size 100 will tend to be more balanced and to vary much less. You can understand this very well if you think in extremis. If you use the largest possible sample size, which is the population size, samples will not vary at all. You will be picking the whole population again and again. There are many ways of understanding intuitively that the larger the sample size, the smaller the variability of the samples, and the smaller the variability of the sampling distribution of sample means. Therefore, the sample size must appear in the denominator of the standard error. The fact that there is a square root here is not so intuitive. You must remember it. This mathematical model is analytically proven to be valid with the help of a very important theorem called the central limit theorem. It is not clear if it was called central because it speaks about the center, that's to say the mean, or because it is so important, central in the sense of paramount. What is clear is that it is called limit because it speaks about the limit, that's to say about the long run. If you average the means of these 4 samples, here you have it, you get 20.8, which does not equal the population mean. But if we were able to pick all the possible samples of size 100 and average all their means together, we would get 22. Alternatively, if we pick more and more samples and we average all their means, at some point that average will be almost exactly 22. And the standard deviation of those means will be almost exactly 0.3. That's the idea of limit. It is worth to stress that here we are working with many means. First, we have the mean in the population, the parameter mu. Then we have the mean in one particular sample, the statistic x bar. We can get many like this by picking more and more samples. And finally, we have the mean of all these means. That's to say, the mean of the statistic mean. In Chapter 3, Part A, Measures of Center, I said that there are 3 common notations for 3 different concepts of mean. Here we have the 3 of them together. What the central limit theorem says, among other things, is that the mean of the statistic mean equals the mean in the population. When something like this happens, when the expected value of a statistic equals the parameter in the population, we say that the statistic is unbiased. In Chapter 7, we saw that the statistic proportion is unbiased, and now we are seeing that the statistic mean is also unbiased. You may think that all the statistics fluctuate normally around the parameter, and therefore all are unbiased. This is not true. The simplest counterexample would be the range. The range in a sample cannot be greater than the range in the whole population, and most of the time it is way smaller. Therefore, no matter how many samples you pick, if you average all their ranges, you will never get the range in the population, In general, the measures of spread have biased statistics, unless we modify the formula, which is what we do with the variance. I spoke about the unbiased variance in Chapter 3, Part C, Measures of Spread. Even the measures of center have usually biased statistics. The median is also biased. If you pick more and more samples and you average their medians, you don't get the median in the population. Before finishing this theoretical part, two last comments. First, what's the shape of the distribution of H's in the college? We studied things like this in Chapter 2, Analyzing and Representing Data with Graphs. This distribution should be right-skewed. Most college students are between 18 and 24 years old, and there will be a long tail with students that are 25, 35, 45, or even older. And then we have here a very interesting phenomenon. While the population is right-skewed, the sampling distribution of sample means is perfectly normal. It is not right-skewed. This is supposed to be counterintuitive or amazing, and it is part of the superpower of the central limit theorem. For this phenomenon to be true, the sample size must be large enough. The stronger the skewness in the population, the larger the sample size must be for the sampling distribution of sample means to be normal. Usually, books say that a sample size greater than 25 or 30 or 40 is enough to absorb, so to speak, any possible skewness and to have here a normal distribution. As always, the samples must be random and small relative to the population. In other words, if in this college, instead of picking samples of size 100, we pick samples of size 7 or 12, we will see that this distribution of sample means is also right-skewed. However, if the variable of interest is normally distributed in the population, then the sample size doesn't matter so much. For any sample size, the sampling distribution of sample means will follow a bell-shaped. That's why when we cannot use big samples, we must check normality. Checking normality means trying to figure out if the variable of interest is normally distributed in the population. In this course, we will not study in detail methods to check normality. We will either assume that the population meets normality or work with big sample size. But you are expected to present the possible lack of normality as an objection to the use of this method if the sample size is small. The second and last comment is that many authors introduce the central limit theorem to prove the validity of the normal model that we saw in Chapter 7 for the sampling distribution of sample proportions. I didn't mention anything then because the validity of that model can be implied directly from the validity of the binomial model. However, it is worth to mention now that a proportion can be understood as a particular case of mean, and what we saw in Chapters 7 and 8 can be understood as a particular case of this Chapter 9 and this central limit theorem. If you have successes and failures, and you call the success 1 and the failure 0, the mean of those zeros and ones equals the proportion of successes, and all this model for a mean becomes this other model for a proportion. Some books teach first this theory for the mean, and from it they deduce the model for a proportion. In my case, I preferred an inductive approach from this particular case to the more general version. Let's answer now letter B. If we pick one more random sample of size 100, what's the probability that in this sample the average age is greater than 23 years? The sample size is greater than 30, the sample is random and small compared to the population, thus the normal model is valid. The sampling distribution of sample means will follow approximately a normal distribution with a mean of 22 and a standard deviation of 0.3. if you put these parameters in a normal calculator, the probability of the statistic mean being greater than 23 equals 0.0004. This brings an interesting observation, that students tend to overestimate the variability of the sample means. When I do the dramatization of a simulation with my students, they gave me samples with means like 19.5, 23.7, 18.8. This is not realistic. Usually, you would have to pick thousands and thousands of random samples before seeing one with a mean like 18.8 or 23.7. Even a sample mean of 23, which is only 1 year above the population mean, is so hard to get. Imagine 23.7 or 18.8. In other words, when the sample is big, the mean of a random sample is usually very close to the population mean, closer than many people's intuition would say. In exercise 2, we want to test if the average life of a new bulb is more than 2000 hours. We pick a random sample of 50 bulbs and the mean life in this sample is 2100 hours, with a sample standard deviation of 275 hours. Letter A. Conduct a hypothesis test. The first step is setting up the hypothesis. The null is the equality, the mean equals 2000, and the alternative is the inequality, the mean is greater than 2000. Second step, selecting the mathematical model. The sample is bigger than 30, random, and small relative to the population. Therefore, the sampling distribution of sample means will follow approximately a normal distribution with a mean of 2000, here we are using the hypothesis, and a standard deviation given by this formula. And here we have the classical situation. This is the standard deviation in the population, but we don't know the population standard deviation, and we don't have any hypothesis about this. So what do you think we are going to put here? You probably guessed right. We are going to use the standard deviation in the sample in lieu of the standard deviation in the population. And we get this approximate normal model. However, you can see that here I crossed out the n for normal. What happens is that when we use the sample standard deviation in lieu of the population standard deviation, we can get a better model if we adjust a bit the normal distribution. This kind of adjusted normal is called a student or t-distribution. Here you see in black a normal distribution and in colors t-distributions. The main difference is that in a t-distribution, the extreme values are a little bit more likely. As a consequence, the middle values are a little bit less likely. That's why we use the t-distribution in situations in which our statistic varies more than usually. These situations can be summarized in two cases. When we use a sample standard deviation in lieu of the population standard deviation, and when the sample size is small. The sample standard deviation varies from sample to sample, so using it adds a plus of variability. Also, we explained before that small samples are more likely to have extreme values. So if we pick a small sample, using the t-distribution provides better estimations. Indeed, the sample size is what matters the most, because the t is a family of distributions. It has what we call degrees of freedom. The degrees of freedom equals the sample size minus 1. You can see here that as the degrees of freedom increase, the t becomes more and more similar to the normal. In the limit, the t would equal the normal. The last important difference is that the t-distribution works only with standardized scores. You cannot select one or another mean or standard deviations. Its sole parameter is the degrees of freedom. What follows a t-distribution is not exactly the sample means, but this statistic called t-stat. In other words, here you must get the t-stat, which is the same as the c-score, but we call it t because it is used in a t-distribution. It is the observed value minus the hypothesized value all over the standard error, in this case 2.57. With this t-stat, we can get the p-value. What's the probability that the sample mean equals 2100 or more than 2100 if it is true that the population mean equals 2000? In other words, what's the probability of a t-stat equal to or greater than 2.57 if we work with 49 degrees of freedom? A t-table or a t-calculator will tell you that this is 0.0066. Since this p-value is so small, the conclusion is this study provides very strong evidence that the average life of the new bulb is greater than 2000 hours. The positive difference of 100 hours observed in the sample is statistically significant. P-value equals 0.0066. Letter B. Complement your hypothesis test with a 95% confidence interval. For 95% confidence, we need to use a margin of error of 2 standard errors. Be careful, this multiplier in the t-model usually is not the same as in the normal model. In this case, it seems the same because we are using 49 degrees of freedom, but we must use a t-table or a t-calculator to get the right multiplier associated to the confidence level that we want. Indeed, in a normal model, it was more precisely 1.96, and here it is 2.01. This gives a margin of error of 77.78. We added to and subtracted from the value observed in the sample, and we get an interval from 2022.2 to 2177.8. This interval supports the producer's expectation and gives us more information. We are 95% confident that the average life of the new bulb is between 2022.2 hours and 2177.8 hours.